Hello, everybody. It's Mike Hochella. I'm sure Paul's already taken the time to introduce me. Let me say before I start on the science here that I really appreciate the opportunity to do this lecture for you today. I have to thank Jeffrey Greathouse, the current president of the Clay Mineralogical Society, for this invitation. And this probably was Paul's idea. He asked me over 2 years ago to do this pioneer lecture. I could have done it and actually been in attendance last year, but this year it just wasn't possible with my travel schedule. So I really hate to do this remotely and not even physically present when you're going to be actually watching this. It's still a great, great pleasure to do this for you. Speaking of Paul, I have to say that I've admired his work for some time, and to show that, I was writing a paper for Science Magazine 2 years ago. Well, it's more like three now. And I asked Paul to be a co-author because I admire his work so much, and he added so much to that paper. Paul, I really appreciate that very much. And for all of you there, if you haven't looked at Paul's book, Clays in the Critical Zone, published a couple of years ago, published by, I believe, Cambridge University Press, um, buy a copy. Teach from it, learn from it. It's a really great book and goes along with all the very nice papers he's written over the years. So thanks, Paul. It's a real pleasure to work with you. Um, I want you to read my title again. Using atomic structure, property, relationships to understand environmental Earth. I've actually been thinking about this, believe it or not, this is true, for 50 years, actually 51 to be exact, which was my freshman year in college. I feel just as young as I did back then, believe it or not. I sure don't look like I used to, but I'm just as turned on by this sentence as I was, or this title as I was then. And what I'm going to do in this lecture, you've been at the conference the whole week. This is the last day. Listen to so many talks. I'm going to give you a lecture light. I want you to just sit back, relax, hear this overview of what I thought about this title 50 years ago. And then I have an example of the hundreds of papers we published and the probably thousands by now, talks I've given in, I think, 28 countries at my last count. I, this has changed in my life, this title, and I'm going to give you an example, just snippets of what we've done 50 years ago, 40 years ago, 30, 20, 10, and then in the last 5. And I want you to see how this has evolved in my mind, and it might be useful for you to think about your own career in this regard. So even if you don't have a lot to do with this kind of science, that's fine. But it can relate to what I know it can relate to any scientist. So have fun listening to this, and I promise not to take more than 40 minutes on this lecture. All right, let's see if I hope you can see my pointer there. Let's go to the next slide. My favorite cartoon. This goes back 20 or 30 or more years. Gary Larson cartoon. I love Gary Larson. You can see the picture of this early microscope, as it says at the bottom, and the two scientists doing their thing here, which is just hilarious, but I think has a lot of meaning. I had to show you that first. All right. This is where I was 51 years ago. I was unbelievably transfixed by the pencil lead, which is actually just carbon, that you see on the left, and then the diamond here on the right, and that they were made of the same material, but their atomic structure was different. And the properties, therefore, in this case especially, are dramatically different. Any property you choose, the properties are dramatically different on both ends of the spectrum. It just fascinated me. And you might think, great, I mean, everybody knows this. This is something you learn as a freshman in college, maybe even in high school. Like, so what's the big deal? Well, I'll show you what the big deal is. That continues to this day, and is worthy of a Nobel Prize. So on the left here, you see the structure of diamond. Like, here's a carbon atom here, and it's tetrahedrally coordinated with 4 other diamonds. And a chemist would call that a sp3 hybrid bond, and I'm sure you all know what that is. And then you go to graphite here on the right, which is the pencil lead, and you see the well-known sheet structure that reminds us of clays and other various other oxides and other structures that are sheet, like sulfides do this, sulfates do this. Um, Most inorganic chemistry materials have sheet structures. Well, carbon does too, and here it is. You stack them up and you get graphite. Here's where it becomes really interesting. If you just take that one sheet and check it out, you will find that it's, first of all, it's called graphene, and secondly, it's a totally hyped 2D matrix of carbon atoms arranged, in a honeycomb kind of lattice. And listen to this: it's the lightest, the strongest, the thinnest material known. And there are other materials that are as this thin, one atomic layer thick, but no thinner, of course. Um, and so it has the best, heat and electrical conduction that have ever been known, and the list goes on and on. And so the two people that I'm afraid my picture is covering it up, but there are two physicists, Andre Geim and who's from England, and Kostya. And I'm going to not say this correctly, but Novoselov from Russia, and they won the 2010 Nobel Prize for being the most impactful scientists to understand the be able to work with one sheet and to understand its properties. And so here we are in 2022, and 2 years ago was the last numbers I have. 2 years ago, 2020, there were 100,000 publications in that 1 year on this material, on graphene, because it has such great properties and such great applications. 100,000 in 1 year. And it hit a peak in 2017 when there were 250,000 publications on graphene. Can you imagine? I mean, that's all of Earth science put together, way more, just on this one material. So, my thoughts 50 years ago are not trivial, and they're not trivial today. These materials are just unbelievably interesting. So, keep that in mind. All right, we're going to really jump over here. That was 50 years ago. This goes back 40 years ago in my life of science. And it was when I was a PhD student or candidate at Stanford. And we see here that these black smokers or hydrothermal vents were first discovered in 1979 on the East Pacific Rise, a spreading center in the Eastern Pacific at 21 degrees north latitude. And since that time, they've discovered these hydrothermal vents in many oceans at spreading centers, obviously, and have studied them a lot. Why am I showing them to you here? Because in this, what seems to be like black smoke jetting out at 9 meters per second, because these fluids are over 300 degrees Celsius, and the seawater right here is 2 degrees Celsius. So the buoyancy is unbelievable, and these things are just like a rocket ship jetting out. And in here, it's just filled with really interesting nanomaterials, some of which are, here we go, graphene and graphite are in this material, only recently discovered by George Luther and Emily Estes, who I've been working with and publishing with lately. Just really great scientists. Emily's at Texas A&M. George has been for many years at Delaware. And their insight into this, and if I could help them even a little, like I think I do, this is just so fascinating. The mineral that's deep in these pipes, in this hydrothermal plumbing system, that makes a big difference here, and it allows seawater that's heated up by magma chambers that are deep in the oceanic crust here, able to leach metals out of the basalt, is this mineral. And this is where I come in again. So here you can see me as a second author, and here's the first author in this GCA paper and this octacrystallographica paper on this material that is forming in that hydrothermal system. We did not discover it, but it was sort of a mystery thing. What we did was, when I was a graduate student, which was not anything close to my dissertation, but I knew how to do it with Keith and Bernard, and we solved the atomic structure of this material. It's a manganese sulfate, manganese hydroxide hydrate mineral. And when this mineral forms, as you would with a clay, when you're forming clays, you're taking up some water and a lot of OH. And in often cases, you're acidifying the surrounding water. And so when this mineral forms in the hydrothermal system, and it does because it's retrograde soluble, so as the temperature goes up, it becomes less soluble and crystallizes. And the pH of the hydrothermal solution goes way down, becomes very acidic, and you start leaching metals out, and that's what brings the metals up into the bottom ocean. And so by solving the atomic structure, we were able to give the exact chemistry of this phase and its geochemistry as in crystal chemistry, as we have in this second paper. And this is what the atomic structure looks like. This is a stereo pair, left and right. If your left eye can just look at that image and your right eye at that image, you'll see it in 3 dimensions. Good luck. I can sort of do it, but not really well. But you see it's a complex structure, but we solved it. And then we know exactly what the chemistry was. And the rest is history. So again, this is a property of a end structure relationship, like I started with my title, and it has a vast, even much more than we even realized, environmental implication, because these solutions coming out of these vents are changing the chemistry of the ocean bottoms. And now it's known that that chemistry change goes up to the mid-ocean levels, becomes a very important nutrient for living things, and on like that. So there you go. Okay, next example is, see, this is now, we're up to 1990, so now it's 30 years ago. And Susan Stipp, who's a very famous professor in Denmark, and she did her PhD with me at Stanford when I was a young professor there. She has had a magnificent career since, is more famous than ever. And we were working on at the time the surface structure of calcite and its interaction with the outside world, like fluids that are around it, because this is when I was in my surface science stage. But it's going to be a structure-property relationship, and it's going to have environmental implications. And so here you have, instead of using X-rays like we used to solve the previous structure, we're using electrons, very low energy electrons, which are impacting the surface of the calcite, diffracting off, just like the X-rays diffract, the way electrons diffract too. But this is surface diffraction only, because the energy of the electrons are very, very low. So this is a diffraction pattern. These dots are diffraction pattern dots of electrons being scattered off the surface. And the pattern of these dots, these diffraction maxima, and their spacing and their symmetry gives us the crystal structure of the calcite surface. And so it allowed us to determine the structure of the calcite surface. And this paper, 30 years old, is still being cited today, something like 30 or 40 times a year. It's really remarkable that people are still using this. And for example, in this picture, cadmium, which is very toxic to humans, when it's in solution and it's interacting with the calcite surface, and you do surface spectroscopy, you'll see these peaks. These are photoelectron peaks using XPS, X-ray photoelectron spectroscopy. These are 2 peaks from cadmium, and so they're on the surface. But if you just let that surface sit for a while, and you do the spectrum again, the cadmium signal is definitely going away. And if you wait even longer, this will be flat. It'll be noisy, but it will be flat. Where did the cadmium go? We've actually proven that the cadmium didn't come off the surface. It's actually gone into the calcite, so deep, a number of nanometers or more deep, up to microns, that it's not observed by surface-sensitive spectra like XPS. So these peaks go away. So, again, it's something that, is the cadmium going to come off the surface? Is it going to go into the crystal, for goodness sakes, at room temperature and pressure? Does that really happen? Well, yes, it happens. And surfaces are very dynamic. They are not static. That's where all the reactions are happening. And in this case, cadmium is actually moving into these solid state materials. So again, a structure-property relationship that has to do with environmental science. All right, so let's go to the next example. Again, this is now 20 years ago. And so this is something I did with Udo Becker. Who's now these are former PhD students of mine at Stanford, and then I moved to Virginia Tech because we couldn't afford to live in the Bay. We could not afford to live in the Bay Area, and I really miss Stanford, but Virginia Tech's a great university too. So we moved there. We raised our family there, and we were very happy doing it. But I have so many friends. Gordon Brown was my advisor there, and I'm closer to him than ever. And Stanford is amazing. Virginia Tech is amazing. And so Kevin Rosso and Udo finished with me at Virginia Tech, and it's a real pleasure to have worked with them. So yeah, Udo's at University of Michigan. Kevin's at Pacific Northwest National Laboratory, where I also work now, and they're both absolutely world-class scientists. And so we were looking at a semiconducting mineral surface. We're going to look at pyrite here, and talk about this proximity effect, but let's just go to the chase here, the bottom line. So now we're looking at electrons, again, moving in and out of surfaces, but not in a diffraction way, in a tunneling way, like tunneling physics. And with a scanning tunneling microscope, you can actually see the atoms on the surface. No kidding. Each of these bumps represents a single iron atom on the pyrite surface, which is undergoing oxidation, and eventually it would create in the environment acid mine drainage, which is why we study these things. And just to show you here, again, just looking at the very bottom line, these spectra, this one's calculated, this one is observed on the surface using our scanning tunneling instrument. The spectra of the valence electron properties here are just energy distributions up here, is where my pointer is, and then down in the conduction band of the material. So it's a conduction band here, valence band up here. So these are, sorry, I got that backwards. Oh, what am I talking about? This is below the Fermi level. So over here on the left, these peaks are the valence band. So these are the electrons that are involved in bonding and non-bonding of the surface. And over here on the right, in the conduction band, these are actually moving. These electrons are mobile in the material. So you can actually get atomic level spectra of what these atoms are doing. The sulfur atoms are in here too. We're not tunneling to them right now, so they're invisible, but they're sort of right where I have the pointer right now. There's an iron atom with a sulfur more or less in between. So when you can do these kinds of things, which are repeated here on the left, you can actually come up with models and ab initio calculations of what the oxidation of the sulfide to now oxidized materials on the surface that create acidity and acid mine drainage, exactly what these reactions are. Again, structure property relationships. These are at the surface, again, and it's impacting the environment. So that was then 20 years ago. I got really even more serious about this. So if you look at in the last 20 years, if you look at the the Earth system science field, I always felt that there are a lot of pieces of the puzzle that have been put in place in Earth system science: the atmosphere, the hydrosphere, the rocks and minerals, the soils where all the clays are, or most of them, the rivers, the groundwater, the ocean water. Did I mention the atmosphere too? This is Earth system science, and a lot of the pieces of the puzzles have been put together. That's how we get the fantastic models that we use today to, for example, look at climate in the future. But the one part that I always thought was missing was the Earth's nanomaterials. And so for the last 20 to 25 years, I've really concentrated my career in this area here on the nanomaterials of the Earth and how it affects. In fact, the science paper that I was talking about with Paul was a co-author. We wrote one in 2019 and an earlier one in 2008, both appearing in the same journal and have been cited a lot, are how the Earth's nanomaterials affect the whole planet. So now I'm moving my environment to the whole planet, not just local or regional, but now global. And so, for example, if you look from a nano perspective, here's how we think of it. Take, take iron oxide. If you put iron oxide in solution and the iron is truly dissolved, as you can see here, where I'm pointing to, there's an iron atom. It's coordinated with 6 water molecules, which are highly labile, by the way. You know, it's in water. The iron is that these water molecules are switching in and out of coordination with iron very quickly, of course. So it's pretty much on average octahedrally coordinated with iron in solution. This is truly dissolved. Now notice that, as you would all know, this is an octahedra. So let's just give the octahedra right here. And if you start linking these octahedra together to make maybe 6 across. So it's basically, here's 1 nanometer for scale. So this nanoparticle is only a nanometer across. And it has this many octahedra of these things. And you can count them. And I think, you know, what we see in nature is that it might be 2 layers thick. So you take the number of octahedra here, like 15 or whatever it is, 20, and or not that many, maybe 15, and then you double it, maybe 30. That's a nanoparticle. Okay. You do it some more, and you get something this big. Now you know we call that nanohematite. We call this nanohematite. Now this thing is like 5 or 6 nanometers across. And do we see these? Absolutely, we do. We see these in soils. We see these in river water. We see them going to the oceans. You know, when you get a really big crystal, that's what we're used to seeing. Rarely see these. People don't normally look for them. To actually see these, you need like a $3 million electron microscope, but that's what we do. So we became well known because we found these things, and we said, okay, now, so, you know, when a chemist comes along and they go, well, like a water chemist, like I am too, but I come along, or anybody would come along, and they go, well, this is dissolved, but oh, it made it through my 0.22 micron filter, so I'm going to call that iron dissolved too. Well, wait a minute. I would call this truly dissolved. To me, this is not dissolved. This is a small mineral particle. And the properties of the iron oxide here and the iron oxide here, I would guess, would be completely different. And I was right. I mean, they are completely different. And sure, this is going to go through a 0.22 micron filter, because 0.22 microns is 220 nanometers. This is easily going to go through that filter, and you can't think of it as a dissolved species. It's not, and it has its own very specific properties. Now, here's where nanoscience becomes really interesting. When you take it this size versus this size, they're different again. In fact, they can be dramatically different again. And so there's a whole spectrum of differences here in properties until you get up to what is considered bulk. And for hematite, as best as we can tell over many years of study, that when these particles, these nanoparticles, get in the range of 20 to 30 nanometers, most of their properties become bulk-like. You have a lot more surface area, of course, still being that small, but at least the properties are bulk-like. The properties of this are way different than the bulk, this even more so different, and these, of course, very different as well. So there you go. So let's go on now to something that was only about 10 years ago. So now we're just 10 years ago. And the one example of many, many I could give you, as I could have in any of these time periods, I'm just cherry picking example here and there. This is about an iron hydroxy sulfate mineral called Schwartmanite. Many of you are probably familiar with that. And this was done by Rebecca French, a more recent PhD student of mine, who's now a very important government official in Connecticut, and she still has environmental science for the state of Connecticut in the United States. And she did her, and then Manu Caraballo, who did a postdoc with us around that time, and we're still in very close touch, and he's back at his university in Huelva, Spain. And in that area is the headwaters of the Rio Tinto, the Red River, which you can see why it's called that. And this and the Odell River, which are actually like streams, they're very small rivers because it's so dry in this part of the world. And these guys flow in the southwestern part of Spain, actually right through here, where I'm pointing now. Here's Spain, here's Portugal, here's the Mediterranean Sea. This is where they empty out into the sea. And the mineral Schwartmanite, which I'll show you in a minute, transports a lot of the heavy metals that come out of these mining areas that are just full of pyrite. Um, and this has been mined since Roman times and still is in a couple of places. Um, the water is acidic enough, and the Schwartmanite can transport very large amounts of, see, things like arsenic and copper to the ocean. And so if you add up all the arsenic that these small rivers bring to the ocean here in the Mediterranean, that accounts for about 1/10% of all the arsenic that makes it to the world's ocean from all the world's rivers. But 1/10%, which is a lot, comes from these tiny rivers that flow in this part of Spain into the Mediterranean. And copper, it's 3% of all the copper that makes it to the oceans from all the rivers in the world. 3% of that copper come from these small rivers. You go, you got to be kidding. So the Schwartmanite, which looks like this, these little nano needles, so these are 100 nanometers for scale, and they're like pincushion, like the tiny pins sticking out into a cushion. It's call it pincushion. These are tiny fibers. And most of the copper and arsenic and zinc and other metals that are in the water are associated with these nanoneedles. And that was never known before Rebecca and Manu and I and some others looked at this. And so again, this is a nanomaterial that's very important in the environment, moving all these metals. And they had proposed an atomic structure for these materials. It turns out not to be correct, because what we find is that, and here there's one needle that's only about, the scale bar is covered up here, I'm so sorry, but that's only about 3 nanometers across. 3 nanometers is really small. There aren't that many atoms along here. And it's mostly amorphous silica and aluminosilicate amorphous materials. And there are goethite-like materials, the iron oxyhydroxide goethite, that are only about, there's a scale bar, what does that say, 5 nanometers, I think is what it says, or 3 nanometers. And you can see the lattice fringes here that the electron microscope is saying, okay, these atoms are ordered. And the spacings here are similar to what you get in goethite, and these are iron rich. And they also are very relatively high in arsenic. So here we have nano parts of these mostly amorphous structures that actually gives the diffraction pattern, the very weak diffraction pattern that this stuff gives. And so this is how this is atomically built, not like the previous model said. And it's when these things get to the ocean and this silica dissolves, we're left with these goethite particles that are high in arsenic. So that's how exists in the ocean. Oh, and I hope, can I play this? I don't know if I can play a movie. There's a movie here, but it's probably not going to play for me. I'm sorry, it's not going to play. Let's see if I do some. No, it's not. Anyway, this is a 3D tomography image of, and as this image spins, you can see these individual 3 to 5 nanometer fibers. It's just absolutely fascinating. Oh, there it goes. Okay, here we go. So there you go. These are 3 to 5 nanometer needles. It's electron tomography, like X-ray tomography would be the scan that you might do on your body. This is electron tomography, and you see things in 3 dimensions. It's really fascinating, but down to the nano level. So here in this last example, I'll go over it very quickly because we're coming up on 40 minutes now. And I think I can give this to you quickly, just give you the bottom line. In the the Proceedings of the National Academy of Sciences published a paper called The Photoelectric Conversion of Earth's Surface via Widespread Iron and Manganese Mineral Coatings, done with Anhui Liu, and a very famous professor in China, probably China's leading mineralogist, Anhui Liu, at Peking University, and myself and a very large group of very talented photochemists and so on and so forth. We had a great time with this, and let's just move on to this slide, which shows that most of you have heard of rock varnishes. These are manganese and iron oxide coatings that rocks get, especially in dry conditions and sometimes very wet conditions. This is the Gobi Desert, where you see these black rock coatings. Those are in China, Gobi Desert. These are in southwest China in these beautiful limestone exposures, which also have mineral coatings on them. And these are lateritic soils, which, as you know, have a lot of iron oxide formation. And all of these semiconducting minerals, these are all semiconducting minerals, very common ones that we all know and love, are exposed to a lot of sun and a lot of uh, interaction with especially the UV of the sun, promoting electrons. As they do in photosynthesis, they do it in inorganic materials too. And you can see here where these coatings, this particular one is a manganese oxide coating, underneath a iron oxide coating, underneath the substrate, which is usually a limestone or some other silicate rock type. And they're only a couple of microns in thickness. And when you look at these with the TEM, sure enough, in this case, we see these tiny, less than 2 nanometers of bernesite, the manganese oxide sheet structure. You see it here, and you see the same lattice fringes here in these particular coatings. These coatings are exceptionally widespread, more so than I ever suspected. And one thing I learned in this project, working with this group, is how extensive they are. The yellow ones are the rock varnishes around the world, as you can see. And the red ones, the rust-colored ones, are the red soils, the lateritic soils that are exposed. And then all the karst terrains. There are exposures of these things in smaller places, but in places where you see colored on the globe, these are really extensive, not very vegetated areas where you get a lot of exposure of these semiconducting minerals. The karst terrains are in the gray. So those are their very vast distributions. When you look at the photochemistry of these layers or these films, you can take a film out, or you can very carefully remove films from rocks, at least small pieces of them, and you can put them between gold electrodes in a lab and study their electronics as you shine light that simulates sunlight on them. I'm not going to go through all this, of course, but the point here is that you can look at the what these semiconducting minerals are doing with especially the UV radiation in terms of promoting taking the photon and promoting electrons from valence to conduction bands and back. And this is the last slide in this part. Before I read the conclusion up here, let me just say that in the organic world, you have photosynthesis. So when the sunlight hits a plant, or the more primitive photosynthetic organisms on the planet are cyanobacteria. Those are believed to have been the first, and then algae after that, and then simple plants. They have what's called this photosystem 2, this PS2 that you have here. And there's a very complex, photosynthetic chemistry is exceptionally complex. It's a whole network of proteins that take in sunlight and make organic matter and produce oxygen as a waste product that we all depend on. But in the first protein along the protein network that is involved in photosystem 2, the cofactor in the first protein, the first enzyme along the way that does photochemistry looks like this. It's a calcium manganese oxide cofactor in a protein to give you this particular enzyme. And when photons hit this cofactor molecule here in the protein, it promotes electrons up into a suitable state to do a lot of photochemistry within a whole line of subsequent enzymes, and the result is production. End result is production of producing biomatter and producing oxygen as a waste. And so we were wondering, if that's the case here, how about sunlight when it hits photoactive minerals like, say in this case, bernesite that you see here? So this would be the inorganic world of photocatalysis, not photosynthesis. We call it photocatalysis. Can we think about both of these in concert? And so, for example, in this Bernesite, just as an example, light hits, energetic light, especially in the UV from the sun, hits an electron in the valence band of one of the states in the valence band of the Bernesite, and it promotes the electron. It annihilates that photon by promoting an electron up into the conduction band of Bernesite. And as that electron relaxes back down, it can do chemistry. For example, it can do chemistry that results in energy for cyanobacteria, as depicted here, through this organic redox couple, which I'm not going to get into because it's a complicated but really cool story. But I won't say anything about it except that this is an energy producing couple, redox couple in living things that uses these electrons, even from minerals. These photoelectrons from minerals have been shown to drive this redox couple here to give energy to these kinds of cells. These electrons, as it's falling back down to its conduction band, can also give up its energy to reduce manganese and iron, for example, and also to generate oxygen from water. And so there's your oxygen byproduct right there. So that's what now you know why it's called photocatalysis. So this is what this paper talked about, and if you're interested, this is a fascinating paper to read. Okay, so I'm going to end here by just going through. By the way, you can get copies of these slides if you email me, which I'll talk about in a second, how you can do that. I can send you this presentation in a relatively small file, PDF file, and then you'll have all the words in these slides. But with everything I've been telling you over the last 50 years of my scientific life, the 50 years of my scientific life, what have we found in this area of the kind of science I do, of putting structure property? As you noticed, every example I gave you used the detailed structure, atomic structure of material, and therefore its properties, and therefore what it does with the environment on local, regional, and global levels. So, whatever, I'll just paraphrase what I'm saying here. Wherever we go, we're finding new things. And it's easy when you go nano because there's just so much so many things that haven't been discovered at this level. So it's sort of science made easy. Without these views on the nanoscale, we'd be missing a vital part of any biogeochemical system, we think. 3 here is in the 21st century, this kind of research will continue to transform our understanding. I think that's pretty clear from my talk. 4 here is the transdisciplinary science. Notice I've been talking about a lot of fields of science here, way outside of earth science, but in combination with earth science, that I'm just really interested in that. So transdisciplinary science is in this regard is essential. Otherwise, our science would only advance ever so slowly, one funeral at a time. Ha ha. And that I didn't come up with that expression. I've heard it years ago. I don't know where it came from. And then finally, for especially younger people in the audience, as you finish this conference today in Istanbul, that my advice to young scientists would be to never stop reinventing yourself without losing your deep foundation. That's clearly the foundation that you have now, and learn how to best participate in team science. Team science is so essential for useful science in the 21st century. So questions or comments? I'm sorry I can't answer now, but you can look me up really quickly and easily. In fact, if you just Google my last name, for better or worse, I'll be the first many hits, and in any of these things you can probably get a hold of me, or just look me up on Google Scholar for looking up the papers we've done and how to find them, my email, and so on and so forth. Nano Earth is the center I started at Virginia Tech. It's funded by the National Science Foundation in the United States. It's for helping people that are just starting in nano and the earth and environmental things, or just environmental things where you need to look at small things. We can help. You can contact us. Just put into Google Nano Earth, and this is what comes up first, and just click on it and off you go. I'm the founder of this, but no longer the director because I'm trying to retire. So other people are very capable now running this center and staffing this center. So please make use of it if you can. Thank you so very much. It's been a great pleasure, and I hope to see you in the future. Thanks a lot. Bye-bye.